Good morning all. Today we will discuss with the tunnel diode. Okay. So we have been seeing the various devices which are power semiconductor devices which are widely used. So normal PN junction diode you are familiar. So in PN junction diode we are having, so here we are having two terminals. Okay, the same only here also we are having the two terminals. One is anode and cathode. Anode is termed to be the positive terminal, is termed to be anode, and the negative terminal is termed to be cathode. Okay, so here mainly when we are talking about tunnel diode, it is a heavily doped normal PN junction diode. Okay, so this heavily doped normal PN junction diode is termed to be the tunnel diode. Okay, so the how it is heavily doped, the width of the depletion layer is very small. Width of the depletion layer is very small, and more normally you will be making germanium and gallium arsenide is used for this tunnel diode. Okay, so why this name? Here it is using, mainly it is using the tunneling phenomenon. That is why hence it is named to be tunnel diode. Okay, so you can see the circuit symbol of the tunnel diode. Okay, so here the concentration, the impurity concentration will be more. Moreover, decreased impurity concentration is more in the PN junction, and decreased depletion width will be very less. Okay, so the barrier potential reduces. Okay, so at that time what will happen now, once your breakdown is occurring, the charge, either the electrons have to move from n side to p side, or the holes have to move from p side to n side. Okay, so this will be, the charge carriers will be penetrate. Normally it is not that it is overcoming, not even to overcome the barrier potential, but it is penetrating to the junction at a speed of very high, the speed of the light. Okay, the so it is penetrating through from one region to another region by making a tunnel, even though it is not having the energy to overcome the barrier potential, since the concentration is more. When you are giving supply, when you are triggering the device, or when biasing is happen, at that time the charge carriers will move through the junction at the speed of light, making a tunneling phenomenon. Hence it is named, hence the name, it is called to be tunneling. This phenomenon is termed to be tunneling. Okay, hence it is the name. Okay, so classically, at least and according to quantum mechanism, there is a finite probability that it can penetrate to the barrier for the width. Okay, so this phenomenon is called to be tunnel, and hence the name, it is termed to be tunnel diode. Okay, it is not climbing, the charge carriers are not climbing through the barrier potential, but instead of that it is making a path, tunnel like structure, it is making a path, and the charge carriers will move from the one region to another region. Okay, so this is a highly doped PN junction diode. Okay, so at the starting time, what will happen, once it is, so at that time, the when you are coming for the characteristics of the tunnel diode, its forward characteristics, that is the its forward current will increase to a peak value, then the negative resistance region will be happening, so then it will decrease, and then again it will increase. So this decrease in region is termed to be the negative resistance region in the case of the tunnel diode. Okay, so how this process is happening, when you are explaining in terms of the energy band diagram, this is the normal diagram where you are having the Fermi level or the equilibrium level will be same. Okay, so here you will be having the conduction band, and here you are having the valence band. Okay, so once under zero bias condition, so this is the structure at which we are having the zero current on the IV diagram. So all when you are having zero bias condition, the Fermi level will be at the equilibrium state. Now we are giving a small forward voltage. Once you are giving the small forward voltage, from here, from the conduction band to valence band, the electrons will start to move from here to here. Okay, making, so electron flow will be moving. So when the maximum tunneling current is, so at that time the current value is also increasing, so the maximum tunneling current is happening, what will happen, the more electrons are moving from this side to conduction side to valence side, maximum number of electrons in the n region, that is your conduct n region are move towards the p region. Okay, so at that time the tunneling current will also be maximum. Again, when after that the current value is starting to decrease. So when here the flow of the electrons, actually how it is happening, the flow of the electrons from the n region to p region is also very less. Okay, at that time your tunneling current is again decreasing. So again, when you are giving at higher level of forward voltage, totally this is upside. Okay, so hereafter the no electrons in the n side are directly opposite to the empty states in the p side. Okay, at that time the tunneling current is zero. So normally at that time the tunneling current will start to decrease. Okay, so these are the stages when happening in the forward bias. During reverse bias, what will happen, the electrons from your valence band will start moving towards your conduction band. Okay, from this region to this region, electrons tunnel directly from the p region and in the p region to n region. Okay, the reverse bias current increases rapidly with the reverse bias voltage. Okay, so this is your tunnel diagram. So here you can see the equivalent. This is the equivalent circuit of the tunnel diagram when you are giving the negative bias in the negative bias resistance region. Hence the equivalent circuit it is used. It is just like a reduced parallel combination of the junction capacitance and junction capacitance and negative resistance. Okay, so this and the negative resistance. So this is how, so the tunnel diode is also widely used for the various switching power applications. Okay, thank you all.